Okay, so this is the solution to Chapter 11, number 26. I will also do Chapter 11, number 27. So just be patient with my handwriting on the screen. We'll do our best. So we have, you can read the problem yourself. I'm going to save some space. The standard deviation is 2.8 inches. Okay. The mu, the mean, is 70 inches. And we don't know this, okay? You know, in this chapter, if you read it or did the video, you know what this means. So I'm going to assume that you have looked at the video. So this looks like this when you write it out. To normalize this data, you use the mean and the standard deviation over the square root of the number of observations of the number of people that you have. That's what the N stands for. Okay? So in part A, we're looking for the probability that the H, what we're looking for, the heights, is between 69 inches. So we write it like this. There's our H. And 71 inches. Okay? So that looks like this when we put it in a formula. 69 less than H less than 71. Let me erase this thing here. Let's do that again. Okay, I'll do that again. So that the P is, this said probability. Probability is less than 71 inches. Okay, 71 inches. So that's what that looks like. So to normalize this, maybe I should just print. We're going to normalize it to a z-score. Okay, and if you, this is from chapter 3. On page 77. All right, so we keep doing this. Now, if you remember how to normalize this, is that we're going to do the probability, because we're going to make it into z-scores. And to make it into z-scores, 69 minus 70, here's that 70 right here, and divided by the standard deviation of 2.8. That's going to be less than the z-score, and that's going to be less than, now we take this 71 over here, this was a 71, or this 71 here, 71 minus 70, and divide that by 2.8. Okay, and that looks like this. The P is negative 0.36, and that's less than Z, and that's less than 0.30. Okay, so that's what you get when you do this calculation, right? So now we continue. So I have to go to another page here. So I'm going to save this, and then I'm going to clear it and continue. So if you remember from what the page we had before, we had this P, we had negative 0.36 is less than Z, which is less than 0.36. Those are from table A in the back of the book. Okay? I'm sorry, those were the calculations. Now we go from table A. So you go in the back of the book, or you can go online and find a table of Z-scores. And from the Z-score, we get 0.3594 for this, 0.3594, which is less than Z, which is less than 0.6406. That's from the table. Okay, from the back of the table. So this means 36%, which is less than Z, which is less than 64%. When we subtract these two, that means that there's a 29% probability, because we subtract 64% minus 36%. And that's where we get 29%. So the correct answer, when they ask you, if you choose one student at random, what is the probability that he or she is between 69 and 71 inches tall? The answer is 29%. So if you chose a student, then that would be a 29% chance they would be between 69, which is on the other page, and 71 inches tall. Okay? That's what your answer is. Be sure to be able to explain it. Now I'm going to continue, and I'm going to save this, clear, and now part B. So this is number 26, part B. The question is, you measure 25 students. What is the sampling distribution of their average height? Okay, so I'm going to write something here. So you're going to use the central limit theorem. What the heck is that? Central limit theorem says that any type of data, if you squeeze it enough, I guess you could use that word, then it will come out normal. The more stuff that you use, and that's on page 302, by the way, and you are using because you are using a sampling distribution. That's what this chapter is all about. When you use a sample, the more numbers you have, the more normal it becomes. Okay? So, and this is the key. It's a sampling distribution. 3 exclamation points, folks. That must mean it's quite important. So, I'm going to start this on another page. So, I'm going to save this and then clear it. Okay, so the sampling distribution, that's an N, is mu. That's your average. And the standard deviation over the square root of the number of people you have. And in this case, we have 25 people. Okay, that's the number of students. Okay, so now let's put in the numbers from this problem. 70 is our average, it's our mu. 2.8 is our standard deviation, and we have 25 students. So when you do it out, this N stands for the central limit, the normalization. You get 70 over 2.8, and the square root of 25 is 5. So that looks like this. 70, 0.56. The next step, I'm sorry, that's the answer. I was going to go on the next step, but that's part C. So for part B, this is your answer. The answer is 70 and the distribution 0.56. Again, the question was, you measure 25 students, what is the sampling distribution? That's what the answer comes out to. Part C, what is the probability that the mean height, that's average, or of your sample is between 69 and 71 inches, okay? So, I'm going to start it here. This is similar to part A. Number will be found in height between with the probability that someone will be between 69 and 71 inches. Okay, so this is similar to part A. So here's the setup. I'm going to start a new page, and here we go. Probability, this is how you write it out. Probability, and I'm going to write it in longhand. Probability, see, those of you that are under 50 years old will have no idea what I'm writing, so I'll spell it, I'll say it out. Probability that your X bar, you should know what that means from reading the chapter, average, will be between 69 inches, we'll put little inches there, and 71 inches. And it looks like this. Probability between 69 and your mean is going to be between there, okay? So we do very similar things. Okay, remember from the first part we did this. We did 69 minus mu, which is 70 over 0.56 is less than z. 71, I'm sorry. Let me do that over again so it doesn't look so messy. (71) minus 70 over 0.56. That's what we got in part B, this 0.56, found in part B. That's why we did part B first, found in part B. All right, so that makes that equal to the probability is between negative 1.79 less than z and less than 1. I don't have the number in front of me. I'd have to do the problem. So then 1.79, I think it's 1.79 positive. Okay, so that's less than 1.79. So I'm going to make it a mess over here. Now you have to go to table A. Go to table A, and you're going to work backwards. All right, save, clear, go. So from table A, we get 0.0367. That's now we're going from the percentage to that percentage was negative 1. The p was of negative 1.79 to positive 1.79. 0.0367 is less than z, which is less than 0.963. And if you're not sure, work backwards. That's the best thing. So what you do next is you subtract. Let me get back to my notes here. I'm still here. Okay, then you subtract. Get negative 0.9633, and then I'm sorry, it's 0.9633 minus 0.0367, and you get 93%. Okay, when you subtract these, you get 0.93, so it's 93%. So 93% chance for part C that you will get a person of the height in your sample as between 69 and 71 inches. Okay, so let's go on to the next problem that people have been having questions about as I finish this sentence with a preposition. Don't do that on your paper. Now we are on number 31. Okay, I'm going to use, let me read it out first in case you haven't gotten there. Number 1131 is that you have auto accidents. The number of accidents per week at a hazardous intersection varies with mean 2.2 and standard deviation 1.4. This distribution takes only whole number values, so it is certainly not normal. Okay, in other words, whole numbers, it's like 1, 2, 3, 4, 5. It doesn't take a, it's not half of a car crash or half of an accident. Again, the mean is 2.2, standard deviation is 1.4. A, let X bar be the mean number of accidents per week at the intersection during a year, 52 weeks. What is the approximate distribution of X bar according to the central limit theorem? So we're going to use the central limit theorem to take all of our samples sample means, and we're going to normalize them. Again, that's what the whole idea of the central limit theorem is. If you ever go further in statistics, the central limit theorem is kind of cool because it says that any set of data, you can normalize them and make them into that curve that you saw in chapter 3. Even though, as I continue to speak and write, the original problem is not normal. That's the beauty of this. I know you guys are fascinated about it as I am. That we're going to normalize. We're going to take a bunch of data and we're going to make it into a curve. I'm not drawing the curve because, as you can see, I don't draw too well. Okay, so that's the whole idea. So again, the central limit theorem is to take all of our sample means and normalize them even though the original problem is not normal. That's what this thing does. Cool? Great. I'm glad you agree. So now we're going to go on. So here's our equation again. Again, this is part A, by the way. 1131 part A. We have N is our central limit theorem. Mu is the mean. If we take our standard deviation and divide by the square root of N. So we're going to use this. Mu is 2.2. Standard deviation in this problem is 1.4. And we have 52 accidents. Okay? X bar means approximately this. N 2.2 is your mu, and in comma, 1.4 is your standard deviation. Divide that by the square root of 52. Okay, now when you do this problem, you're going to get this. This equals N 2.2 accidents. That's the average. I mean, I'm sorry, yeah, the mean. And we get 0.1941 accidents. So that's how it's written. That's how it's written. Okay, that's what they're asking for part A. Basically, again, I will say the question was, let X squared, what is the approximate distribution of X bar according to the central limit theorem? This is it, right here. Right here. That's what they're asking, the distribution of 2.2 accidents and 0.1941 accidents. Okay, part B. Part B, the question is, what is the approximate probability that X bar is less than 2? Probability that X bar is less than 2. mark. So now we're going to look at the probability. We're going to say the probability that x bar is less than 2. Yeah, I just wrote it in that form. Probability that your z-score, and you go, okay, you're going to go into the z-score and get it from chapter 3, all right? So it ends up looking like this, is less than negative 1.03. So where did this come from? Remember, to get the z-score, from chapter 3, take this, x bar minus mu, and divided by the standard deviation. And so, in this case, it looks like this. 2 minus 2.2 divided by 1.4, and that equals negative 1.03. So that's where that negative 0.103 comes from, right there. So we have a negative 1.03, negative 1.03. Go to table A. By now you should know where that is, and you get, look it up, 0.1515. Therefore, in math, if you want to be a math geek, those 3 dots mean therefore. There is about 15% chance of having less than 15.15% chance of having less than 2 accidents. Okay, pretty cool, huh? I'm sure you're enamored by now if you're still with me. And then finally we have part 3. So I'm in part C. This is 1131, part C. The question for 1131, part C is, what is the approximate probability that there are fewer than 100 accidents at the intersection in a year? So we restate this in terms of x bar. How the heck do we do that? So we're going to let A, just a variable, is the number of accidents. Number of accidents. I'm calling it A because the first letter of accidents is A. I'm sure that you are enamored by this. I'll put an exclamation point, but just one. So that means that x bar, that's the probability, is the number of accidents in 52 weeks. Okay, so we write it out like this. The probability of A being less than 100, because that's what they asked for, is P is, that's an A by the way, P is x bar. Is it less than 100 divided by 52? That's how it's set up. Get your z-score. And the z-score is probability of 100 over 52 minus mu. I'm sorry, but yeah, and this is all divided by standard deviation. It's a little bit more difficult, so you might have to look at this a few times. Is all this number comes as 1.9223. That's the 100 divided by 52. And we subtract the mu, which is 2.2. And all of this is divided by our standard deviation, which was 0.1941191. So that equals the probability of z being greater than this whole number. Okay, this whole number is negative 1.43. Then you go to table A, and the probability in that table A is 0.070. Yeah, get this out again. Point 0.0764. So that means there is a 7.64% chance of fewer. That was less. That's why we use less than, fewer than 100 accidents in a year. That one's a bit more difficult. So if you have a handle on that, if you have any questions, you know where to go and ask. I do want to add another one here, and that's number 35. So I lied when I said we're only doing 2. We're sampling male students, so that's a problem already because we know what that means. To estimate the mean height of male students on your campus, you will measure an SRS of students. And you know from government data that the heights of the young men in that age group are approximately normal with standard deviation about 2.8 inches. If you did the first test, which you should have, you would have found that this was probably what you were working on. How large of an SRS, that's a standard random sample, it must you take to reduce the standard deviation of the sample mean to 1/2 inch? What the heck does that mean? So let's do number 35. This is a chapter 11, number 35. Okay. All of this means that we need to choose an n big enough. We have to find the n this time, so we're going to work backwards. You need to find the number of people. In other words, if you do a sample and you only ask 5 guys for their heights, that's not big enough to reach what the normal average height would be. So they're finding out how many do you need to find in order for it to be true. So that, I'm going to continue, so that 2.8 is the standard deviation nationally, divided by the square of n, that's the n, is 0.5. Okay? So to help you out, I'm going to ask this question. What does this mean? Or where did it come from? Okay? And the answer is, remember that the standard deviation of all the means of a sample is found like this. Standard deviation is equal to your sample, the standard deviation of the whole group divided by the number of people that you have. This comes from the central limit theorem, and which is n. Let me make this, I'm going to write it here. N, which is mu, your mean, divided by the standard deviation and the number of things that you have. See, it looks like that. So I'm going to continue writing and talking here. So in this sample, in this problem, we want our standard deviation of the sample. Remember, we're taking a sample of a bunch of guys in college. Probably some of them are not wearing masks. That's the X bar. That's our sample to be 0.5. That's the one we know it should be. That's the standard nationally. So that's where we get 2.8 divided by the square root of n equals 0.5. So you do some algebra here, okay? And algebra is you cross multiply. So the 2.8 equals 0.5 times the square root of n. You're going to divide both sides by 0.5. 0.5 just to be consistent. Okay, and that equals, you get 5.6 equals the square root of n. So you want n, you don't want the square root of n, so you're going to square both sides. So you're going to square that side, you're going to square that side. So now that looks like 5.6 squared equals n. And when you square 5.6, that means you get 31.36 equals n. Now you can't measure 31.36 guys, so you round it off to 32 men in sample. Okay? That's how you solve the problem. I've had some questions since then about number 36, so I'm going to do number 36. Number 36, the book says, you're sampling male students again to estimate the mean height mu of male students in your campus. You will measure an SRS of, as simple in the sampling of students. You know from government data that the young men are approximately normal with standard deviation about 2.8 inches. You know that. You want your sample mean to estimate mu with an error of no more than 1/2 inch in either direction. A, what standard deviation must X bar B have so that 99.7% of all samples give an X bar within 1/2 inch of mu? This is the 68, 95, 99.7 rule. Okay, so 1136A looks like this. So remember the normal curve. Chapter 3. And the percentages. Okay, so we have the normal curve here. And this is where the mean goes. And you know from here to here, we have 68% of the people, of the population, of our sample, I should say. And then from here to about here, it's 95%. So 95% goes from here to here. And then when you go from here to here, you have 99.7%. 99.7% falls from here to here. Okay, so that should not be brand new to you. Okay, so that's what that looks like. Continuing on. This 99.7% of the observations, the guys you're measuring, they fall within 3 standard deviations. That should not be anything new, within 3 standard deviations. So that's chapter 3. So we want to write 3 times these standard deviations of our thing. So we want this 3 times the standard deviation over our square root of our number, and that equal 0.5. Okay. Again, that means 3 standard deviations have to be within a ½ inch of the mean. We want 99%, not over 99% of the guys to be just a ½ inch of the mean. We don't want all of these basketball players. Okay? So do the math. Remember, the standard deviation of the mean is this central limit theorem. So we're solving for this. Take the equation, put it like this. As not to confuse you. So you write 3 standard deviations has to equal 0.5. Okay? So divide both sides. So it divides both sides by 3. Boom. Your standard deviation has to be 0.5 divided by 3, and that equals 0.16. So the answer is, thus the standard deviation of our averages is 0.16 inches. So now we know. Okay, that means anyone who's over 0.16 inches above, that's going to be our standard deviation for our problem with these guys. Okay, now let's go on to part B. How large an SRS do you need to reduce the standard deviation of X bar to the value you found? So now we have to find out how many people we need so that our standard deviation will be this. Okay, so that's part B. So 36B. I will write it again. We need to choose the number of people. If we don't have enough guys to measure, this ain't gonna work. That's my language. It ain't gonna work. So that 2.8 divided by square root of n has to be 0.16. That's the number we just found. Okay, 0.16. That's our standard deviation. I'm really vehemently pointing to my screen right now, so I hope you can feel it. So solve for square root of n has to be 16.8. Okay? The square root, that means you square the both sides. Square root of n has to be over 16.8. That's when you do this problem out, by the way, okay? Problem out. Square root of n, when you do it by algebra, you'll get square root of n equals 16.8. So square both sides. Write down algebra. Square both sides. So I'm going to do that now. Square that side. Square this side. So n has to be 282.24. Well, you're not going to measure about a quarter of a person. So round it up and measure 283 is your sample size. So again, for this problem, you need to measure 283 guys so that your standard deviation of these 283 will be 0.16 inches, and 99.97% of them will fall within that range. So I hope that helps a little bit. You can follow along with the documents that are part of this answer. I don't know how best to say that, and hopefully this will make a lot of sense. And if not, you know what to do to help yourself is to contact me. Take care.